Welcome to Understand the Math. In this Calculus 1 video, we're tackling two big ideas that you'll see right away in the course: the tangent problem and the velocity problem. I'll teach you all about both of these problems, and we'll walk through an example of each to see how they work in practice. Be sure to download the guided notes to help you follow along step by step. We'll start with learning about the tangent problem and walk through an example. The tangent problem is about finding the slope of the tangent line to a curve at a given point. In this graph, we have a function y is equal to f of x, and we want to find the slope of this tangent line at point P. Before we find the slope of the tangent line, let's make sure we understand what a tangent line is. A tangent line to a curve is a straight line that touches the curve at exactly one point, such as the point P up above, and has the same slope as the curve at that point. Because the two slopes are the same, finding the slope of the tangent line to a curve enables us to find the slope of the curve at that point. Let's now talk about how we can compute the slope of a tangent line. We're going to start with what we can calculate, which is the slope of a secant line, and we abbreviate that by m sub sec. In our graph, we have a curve y is equal to f of x, and we want to find the slope of the tangent line at point P. To the right and left of point P, we have 2 points that we've labeled point Q. The lines connecting points P and Q are called secant lines. The slope of these secant lines is abbreviated as m sub pq, and it's just equal to the change in y, which is right here, divided by the change in x, which is right here. In this series, I'm always going to write formulas in green and put a box around them so that they're easier to find and remember. Now what we're going to do is to find the limiting value of the slope of the secant line as point Q moves along the curve and approaches point P from both the left and from the right. Here's our point P, and then we have our points Q to the right and left of point P. Our points Q are going to travel along the curve and move closer to point P. As they do this, the slope of the secant line eventually equals the slope of the tangent line. We can write this mathematically as m subtangent, that's the slope of the tangent line at point P, is equal to the limit as Q approaches P of the slope of the secant line. This is just the limiting value of the slope of the secant line. We'll be talking a lot about limits in this course. Now that we know how to find the slope of the tangent line, we can find the equation of the tangent line to a curve at a point P, and we're going to notate that point P as x1, y1. The equation of the tangent line is then y minus y1 is equal to slope of the tangent line times x minus x1. This equation is written in what we call point-slope form. I have a video on that if you need to review that concept. Once you find this equation, it's often helpful to write it in this form, which is called slope-intercept form. The reason for that is when you write an equation in this form, you can easily see the slope and the y-intercept. To make things easier, I've written down 3 steps that you can follow to find the equation of the tangent line. We just went through these 3 steps. We first calculated the slope of the secant line, and then we found the slope of the tangent line, and then we used that slope of the tangent line to write the equation of the tangent line. Let's now look at an example. Let's walk through an example of finding the equation of a tangent line to a curve. Suppose we have a point P located at 5, 3, and it lies on the curve y is equal to the square root of x plus 4. We're then told that point Q, located at x comma square root of x plus 4, is some point on the curve. We want to find the equation of the tangent line at point P. I think it's always good to make a graph when you begin this type of a problem so that you can visualize it. I made this graph on Desmos. It's a free graphing tool that I highly recommend using while you're studying calculus. Point P is located here at the point 5, 3, and point Q is going to be located to the right and to the left of point P. Let's write down that P has coordinates 5, 3, and then Q has coordinates x square root of x plus 4. Our first step in finding the equation of the tangent line at point P is to calculate the slope of the secant line. I think it always helps to write down your formula first. Our formula for the slope of the secant line is m sub sec is equal to m PQ, that's just the slope of the secant line between points P and Q, and that's equal to the change in y divided by the change in x. We can find delta y divided by delta x by looking at our points P and Q written in the upper right. Our change in y is going to be the square root of x plus 4 minus 3, all divided by the change in x, which is x minus 5. Our second step then is to calculate the slope of the tangent line. Let's start by writing down that formula. M sub tangent is equal to the limit as Q approaches P of the slope of the secant line. So this is the limit as the x-coordinate of point Q, which is up here on the right in orange, which is x, goes to the x-coordinate of point P, which is 5, of the slope of the secant line. And now we just have to copy down the formula, which we just found, which is the square root of x plus 4 minus 3, all divided by x minus 5. Now here's where the hard work begins. When we compute the slope of the tangent line, we're going to let x approach the point 5. So we have to figure out where x should start. I'm going to start with point Q being to the left of point P. So I'm going to start with x being at the value 4.5. We're then going to calculate the slope of the secant line. What you have to do now is take this x value and put it into this formula. When we do that, we get 0.169048. Now we're going to let x get closer to 5, so I'm going to make a big jump, and I'm going to say x is 4.9. Plug that into the calculator, and you get 0.167132. Now we're going to get closer to 5, so we're going to say x is 4.99, and we get 0.166713. And now let's let x be equal to 4.999. That gives us the slope of the secant line is 0.166636 and then 71. Now we're going to let point Q be to the right of point P. So we can start with x being 5.5. And we'll compute the slope of the secant line just like we did before. We take 5.5, plug it into our formula in green, and we get 0.1644 0.414. Then we let x be 5.1. We get 0.166206. And then x is 5.01. And our slope is 0.166620. And then lastly, our x is 5.001. And we get that the slope of the secant line is 0.1666. That's 4 sixes and then a 2. Now we can find the slope of the tangent line. The slope of our tangent line is going to be what we call the limiting value of the slope of the secant line. As x got closer and closer to 5, our slope of our secant line went to these values. And we can say that those are equal to 0.1666 with the 6's repeating. And you might recognize this number. It's equal to the fraction 1 over 6. So the slope of our tangent line is equal to 1/6. Our last step now is to just write the equation of the tangent line in the form y is equal to mx plus b. This is actually the easiest step. Let's write down our equation in point slope form. Y minus y1 is equal to the slope of the tangent line times x minus x1. Now we're going to plug in that x1, y1 is our point 5, 3, and the slope of our tangent line is equal to 1/6. This gives us y minus 3 is equal to 1/6 x minus 5. Now we want to take this equation and put it in slope-intercept form. We'll pull the 3 over to the right and then multiply out the 1/6. This gives us y is equal to 1/6 x minus 5/6 plus 3. We can think of our 3 as 18 over 6 so that we can better add our fractions. And this gives us y is equal to 1/6 x plus 18 minus 5, which is 13. So we get 13 divided by 6. And that's the equation of our tangent line. Let's now learn about the velocity problem and walk through an example. The velocity problem is about finding the instantaneous velocity of an object at a given time. We can find the instantaneous velocity by first finding the average velocity. These two velocities are related to the slope of the secant line and the slope of the tangent line. Average velocity is usually written as v sub av. It's the slope of the secant line, and it's equal to the change in the position, which is called delta s because s is position, divided by the change in time, and t is our time variable. If our time interval is from t1 to t2, this is equal to s of t2 minus s of t1 divided by t2 minus t1. The instantaneous velocity then is usually written as v, and it's the slope of the tangent line, which is just the limit as t2 goes to t1 of our average velocity. Those are the formulas that you're going to need to know, and I again put them in a green box to make it easier. Let's now walk through an example. Suppose a rock is launched vertically upward from the ground with a speed of 96 feet per second. Neglecting air resistance, the position of the rock is given by y is equal to minus 16t squared plus 96t. I've graphed this function down below. You can see that the rock starts on the ground, goes vertically upward, reaches a maximum height, and then comes back down. We're going to find the average velocity over these given time intervals. Here's our first interval, second, third, fourth, and fifth intervals. Notice that in each of these intervals, our time starts at 1. After we find the average velocity, we are going to estimate the instantaneous velocity when t is equal to 1. We're going to place our point P when t is equal to 1, so that's right here. And then if we look at our time intervals, our first interval goes from 2 to 1 all the way down to our last interval, which goes from 1.001 to 1. So let's go ahead and put point Q on our graph, and we'll put it when t is equal to 2, because that's our first interval. Our average velocity then is going to be the slope of the secant line, and then our instantaneous velocity is going to be the slope of the tangent line at point P. I'm going to write a few things down right here beside our graph because I think it's going to make a little bit more sense. Our time is going to go from T1 to T2, and we're going to let T1 equal 1. I think that's a big point of confusion for students. And then we're going to let T2 vary. So we're going to set that equal to t. We can then write that our average velocity is given by the formula S of T2 minus S of T1, all divided by T2 minus T1. I think it's always good to write down the formula just like you've memorized it. Now we're going to make a change. Our S is our position, and our position in this problem is given by y. So we're going to write this as y of T2, which we just said was t. So this is y of t minus y of T1, which is 1. All divided by T2, which is t, minus T1, which is 1. Our instantaneous velocity is then going to be the limit from T2 to T1 of our average velocity. So this is just going to be the limit as t goes to 1, making that change in notation, of our average velocity. Since we had to continue onto this page, I've rewritten the problem just to make things easier. Let's go ahead and let's highlight that this is what y is going to equal, because we're going to need that. We're going to start with part A. We've already talked about it, so we know what we're going to do. Let's just go ahead and now write down our formula that we had from the previous page. We found that the average velocity was y at t minus y at 1, all divided by t minus 1. Now we're going to plug in what this is. Y at t, looking at our formula highlighted in yellow, is minus 16t squared plus 96t minus y at 1. So this is minus 16 times 1 squared plus 96 times 1. And we're going to divide all of this by t minus 1. Now let's go ahead and simplify. This is minus 16t squared plus 96t. We have a minus a negative, so that's a plus 16, and then we have a minus 96. I want to point out this negative right here. The biggest mistake I see students make is to not carry that minus over to both terms. And all of this is divided by t minus 1. Simplifying further, this gives us minus 16t squared plus 96t minus 80. And that's all divided by t minus 1. Now we need to factor this quadratic. Notice that 16 is common to all three terms. So I'm actually going to take out a minus 16. So we get t squared minus 6t plus 5, because 16 times 5 is equal to 80. And our denominator stays the same, t minus 1. Now we can go ahead and factor. This quadratic factors as t minus 1 times t minus 5. And you can see that our t minus 1 terms are going to cancel. So our average velocity becomes minus 16 times t minus 5. And that's equal to minus 16t plus 80. Let's highlight that because that's what we're going to use for our formula when we compute our average velocity in all 5 of our intervals. Our first interval is from 1 to 2. So we're going to let t equal 2. So our average velocity is just minus 16 times 2, just plugging into our formula highlighted up there in yellow, plus 80. This is minus 32 plus 80. So we go to a value of 48, and we always need to put our units in. Our average velocity is going to be feet per second because it was delta y, which was in terms of feet, divided by delta t, which was in terms of seconds. Now let's look at our second interval. It goes from 1 to 1.5. So t is 1.5. Our average velocity is then minus 16 times 1.5 plus 80. You can throw that into your calculator, and you would get a value of 56 feet per second. Let's now look at our third interval. It goes from 1 to 1.1. We're going to do the same thing. T is equal to 1.1. Our average velocity is then minus 16 times 1.1 plus 80. And this gives us an answer of 62.4 feet per second. Hang with me, we just have 2 more intervals to do. Our fourth interval, we're going to go from 1 to 1.01, so we're getting a lot closer to 1. T is 1.01, and our average velocity is minus 16 times 1.01 plus 80, and this gives us a value of 63.84 feet per second. Now let's look at our last interval. This is from 1 to 1.001. Our t is 1.001, and their average velocity is minus 16 times 1.001 plus 80, and we get a value of 63.99 feet per second. Let's go back up here and let's highlight these answers. Here's our first one, second one, third, fourth, and fifth ones. Now, what we're going to do is estimate the instantaneous velocity when t is equal to 1. Our formula is v is the limit as t goes to 1 of our average velocity. When we look back up and look at our answers that we highlighted in green, we have to find our limiting value. As you look at those numbers, can you see that they are getting closer and closer to 64? So that's actually going to be our instantaneous velocity. So our instantaneous velocity is going to be 64 feet per second. Thanks for watching Understand the Math. Be sure to do lots of practice problems so that you can make sure you understand these concepts.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.